Hey, welcome back, everybody, for more basketball with Mr. Hayes. Anyway, we're going to be continuing to play around with P levels, significance testing, and all of that good stuff. So, let's talk about this. So, same situation as Section 9.1. I claim I can shoot baskets at 80 free throws at 80% level. I ended up shooting, what was it, 63%. So the question is, am I lying or am I not? So if we're going to do a significance test on this, we need two hypotheses. So take a second, hit pause, write out what you think the null hypothesis would be and what the alternate hypothesis would be. You should have come up with a regular hypothesis, or the null hypothesis being p is equal to 0.8, and the alternative hypothesis being p is less than 0.8. The question is, why should it be less than? Because you think I'm a lying, sneaky twit. That's why. Also, the evidence that you have shows that it's less than that. They shot, I think it was, what, 64%. So, with that in the back of your head, you're like, ooh, oops. Yeah, we're going to do skills at some point, don't worry. So, question 2. Would it be appropriate to use a normal distribution model for sampling distribution of p hat to justify your answer? Think about what out of the conditions that we have would double check normalcy. Yes, you. Good. You're right. Large counts. Large counts and proportions will tell us that if as long as we have large counts, we can assume that it's normal. And large counts have to be greater than or equal to 10. And for some reason, I forgot to write that in. So we will do so now. Both of those are greater than or equal to 10. So the missed shots are a little close, but hey, this is less than or equal to. So you know what they call the person who graduated last in their medical school? Doctor. Doesn't matter. You passed. That's good enough. So same thing here. We've got 10 here, 10 here. We're good to go. So what are the other things that we need to check on this? There are two other conditions we need to check. Large counts is one of them, so we can assume everything's normal. We also should be checking. What's the bell going off in the back of your head? Come on. Come on. Yep. Right. Is it random? Which you can assume that they are. And the other one is 10%. Is the sample size that you're having at least 10% of what we have? Ask yourself what that is going to double check. What is that going to give us? What do each of those three conditions give us? Because obviously here, large count gives us that it's normal. What does random do, and what does the 10% rule do? So now that the conditions have been met, we have to find the mean and the standard deviation for this sample. So the mean of p hat shouldn't be a surprise. It's the same thing as p, is 80%. So we are assuming they should have shot 80%. That's what, sorry, I think my mic just almost ate it. That's not good. And then, how do I find standard deviation of p hat? Come on, you know it, you love it. That's right. Square root of p times not p all over n. So in this case, we get this. So we go 80% times 20% divided by 50, root all of that. We get a wonderful 5%. So one standard deviation is about 5.5% away from 80 if I shot 53 of those. So take a second, make sure that that all makes sense. If it doesn't, turn to somebody around you, say, hey, does that make sense? If so, explain it to me. So it says, using the mean and standard deviation you found to label a normal curve. This here, for the most part, you're going to be expected to draw out. And the reason for it is twofold. One, you can use it as a graphic organizer to make sure that you're looking at the right spots, that you're looking at the right side of the curve, et cetera, et cetera. The second part is to also help demonstrate that you know what you're doing. And so it's kind of both of those. So we want a normal curve with a mean of 80% or 0.8 and a standard deviation of 0.045. Your parts down here should be labeled. So a mean of 80. There's my p hat. And then the other thing that you should do here is you're going to mark it. And why did I put it over here? Well, partly, this is what, 16 away? 16.16. And so we know that it's going to be, you know, one standard deviation is here, two standard deviations are here. So that's going to be 12%. So we're not quite at 3% yet, because that's going to give me the, like, around 17. So this is the area that we want. But again, by coloring this in, it does two things. A, we know it's going to be really, really small, because we're past the two standard deviations. And by the way, it's a little hard to see. So you may be reading this as like a negative 1.5D or negative 2.5D. That's actually negative 2 standard deviations. That's not a 5, that's an S. But anyway, so drawing out the standard curve and organizing it, you're going to be like, ooh, should be small. I don't have a lot of area here. And in fact, you can calculate out the z-score. Remember how to do that? And that's the cool thing. You should be feeling like you're pulling things from a whole bunch of different chapters. We've got z-scores from chapter 2. We've got, you know, stuff from chapter 4 from the very beginning of the year. Things from 6. And so anyway, here's your z-score. Your z-score turns out to be a negative 2.86. So the probability, so you're going to look this up, either on your calculator, or you're going to do it off on your z-tables. And to look that up, the probability of making an 80% shooter, so me shooting 80%, at random, shooting 32 out of 50 for a p-hat score of 0.64 or less is a grand total of 0.002. There's 0.2 of a 1% chance that I would have randomly shot 64% from the field or from the free throw line if I truly was an 80% free throw shooter. If I took 50 shots. So as if you didn't need more evidence of me being a liar about it, guess what? Ka-ching. So what conclusion can we make? We have convincing evidence against the null hypothesis. Mr. Hayes shoots free throws at a percentage less than 80%. So notice here we're saying we have convincing evidence against the null hypothesis. Again, remember, we can't prove or disprove that the null hypothesis, or we can't prove that the null hypothesis happens, but we can disprove that it happens. And if we disprove that it happens, then we assume that the alternate hypothesis is true. And that was that. All right. So again, take a thought, look over those, see what you got. Recap. Conditions. You have 3 of them. First one, it needs to be random. If it's not random, it can be influenced. So you're going to look in the writing, or when you design it, that you're going to have it be random. Simple random sample is best. 2. Come on. There we go. You have to have the 10% sample. The sample that you have has to be less than 10% of the population that you do. 3, pardon the yawn, is your normalcy. Large counts. N times P has to be bigger than or equal to 10. N times not P has to be bigger than or equal to 10. Now the rest of this, there's a lot of formulas over here I'm going to warn you about. So, how does t-stat and p-value work? Again, a lot of this is going to be familiar. We're just going to kind of wrap it all up. So, whoa, there's too much there. Whoa. So let's do this. So a couple things. First of all, you have to have a normal curve. We know that by the large counts. So you have a normal curve with a mean value and a standard deviation. The mean value is here. Your mean of p hat is just going to be the assumed p value. So again, remember, we're trying to see if what we're seeing. Remember the premise. We have an assumption about the population. We're taking a look at the sample, and we're saying, what are the chances that the sample could have happened at random if what we assume to be true about the population is true? So that's why that's there. And the standard deviation of p hats, a very familiar looking standard deviation that we're going to set up. Z, you're going to see this a couple different ways. I prefer to write it like this. The reason why I prefer to write it like this is that some places will actually put this whole formula underneath on the bottom. I find that that is somewhat intimidating to a lot of people, not to mention the fact that you already know how this is calculated, so to stick it into a formula, just to stick into the formula makes you feel like you got to memorize something else. Where here, this is a much more natural, again, observation minus the mean divided by standard deviation. That's the definition of z-squared we had. We're just putting it in a slightly different context. But if you do all of this and you calculate out the z, this will lead you to, not my calculator, but to the p-value. Pause when you need to, write things down, take a screenshot. While you're doing that, I would like to remind you to make sure you smash that like button, hit subscribe, share it with your friend, and put that little bell on so that you know when there's a new video coming out. Thanks for coming and playing. You know, the stats sandbox. All right, anyway, that commercial's over. Check your understanding. Census Bureau. Dun, 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 dun. Proportion of high school students who have a part-time job is 25%, according to the U.S. Census Bureau. Administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national number. So she'd like to carry out a test at 5% significance. The administrator selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. Couple of things here to point out. Pull up my highlighter. First of all, she suspects the part-time job is less than the national figure. So that's going to help us get our alternate hypothesis. Random sample, another good thing to know. I thought I hit pause, sorry. Anyway, moving on. So, state the appropriate hypotheses for these. Here we go. And it'll become a shock. Null hypothesis. We're going to assume that what is happening nationally is happening at your school. So the null hypothesis is that p is equal to 0.25. The alternative hypothesis, again, from this statement right here, is that p is less than 0.25. Why? Do we have any evidence supporting this? Yeah, we actually kind of do. Not enough to say, hey, but, you know, in a robust level, but at least enough to say, at least in the right direction. 39 out of the 200 said they work. That's 19.5%. And that's less than the 25% that we want. Or that, you know, is national. So, you're at least, the principle here is at least thinking in the right direction. Conditions. You have 3 of them. I think you've already noticed one. It's random. It's stated as a random sample. Good enough. But do say down here. Is it random? Stated it was a random sample. Check. In fact, let's do this. What else? You're right. Very good. 10% rule. Now, this is interesting. We don't know how many students there are at the school. So we're going to assume that the 200 is less than 10% of all students in the school. So we're assuming that's in this case. So that's check. I mean, certainly at our high school, but for some high schools, that could be the entire population. And last but not least, large counts for normalcy. So 200 times 25% is 50. 100 times 75% is 150. Yes, you have to write both of them down. Both are less than 10%. So our normalcy is good. Check. And again, remember, this actually, what's the 10% rule for? Independence. So long as you have less than 10% of what's going on, you don't have to worry about replacing them. I just realized I never typed this part up. So we will try to do this all together. So first things first, mu of p hat, I know they're ugly hats, I'm sorry, is equal to 0.25. So that's just the standard what we assume the population was. Sigma p hat, if you stick it into the formula from up here, right here, that would give you 0.306. Standard deviation is right around 3%. Let's draw ourselves a little normal curve here. And then, actually, I'm going to use a thinner pen. Wow. That's not bad for using a mouse pad. So you've got right here, 0.25. So you've got the mean of 0.25. And then the number that we're trying to find, which is 0.195, again, remember, because that's 39 out of 200, is roughly 2 standard deviations away. Would be 6, so it's right around 19. So it's right around there. And we want to go less than that, so we would color in this direction over here. You're going to calculate out the z-score. Remember, z is p hat minus p, all divided by the standard deviation. Oh, I forgot one little thing here. Our normalcy curve, you got to list out what you've got. And you're going to go through and you're going to calculate out z. So in this case here, z is equal to p hat minus p, all divided by the standard deviation of p hat. So let's go ahead and type this in here. So that's going to equal, let's see, 0.195 minus 0.25. Oops. All divided by, oops, I don't need underlining there, 0.0306. And so you do all of that magic, bam, you get negative 1.797. And, which is right around negative 1.8, and that's going to lead us to a very nice number. Remember, life's better with sound effects. That's going to give us a number of 0.036. So we have a probability of 3.5%. Now, again, remember, what is our alpha value here? Again, remember, this p-value, capital P-value, is different than this p-value. Other things here, too. Some of you guys, again, might be wanting to say, hey, do we really have to calculate the z-score? Yeah, actually, here they do. They tell you to standardized test statistic. You need the z-score. Standardized test statistic, p-value, p-value. Alpha here, remember, another thing to keep in mind, alpha is 5%. So this is under our 5%. So from there, we're going to write our conclusion. We have convincing evidence against the null hypothesis since 0.036 is less than 0.5. If you really want to get fancy, and I know some of you do, you could also put in, make that alpha, and pop that into symbols. Bam, see? Oops. Put it equal in there too. There we go. So then from there, after you're saying that you have convincing evidence to reject the null hypothesis, you're going to go on to say, we reject the null hypothesis and conclude that the alternative is true, or alternate, I suppose might be a better way to say it. Alternate. It's true, the proportion of students with a part-time job at this school is less than 25%. So again, notice you're saying right here in the first one, we're rejecting it. You are formally saying we're rejecting the null hypothesis and that the alternate would be true. And then you're putting the alternate hypothesis in context. The proportion of students with a part-time job at the school is less than 0.25. All right. So lots there. Should be a good setup for you to get started on section 9.2 and dealing with the proportions of this. I think that's about it. If you have any questions, shoot me an email, or we'll talk about it in class tomorrow. Thanks. Hang in there. Have fun.